Let's begin with one of the most fundamental problem solving technique in computer science, the brute force technique. This approach is exactly what it sounds like. You try every possible solution until you find the correct one. It's never clever but simply and guaranteed to work eventually. Imagine you have forgotten the 4-digit code of your lock. If you try the combination from 0000 to 4444, you will surely unlock it, but possibility only at 10,000th try. The brute force is in action. So, while brute force can solve any solvable problem, it usually not the most efficient, but it's great place to start when you design algorithm. Okay. Here we are going to see about the selection sort, bubble sort, sequential search, closest pair and convex hull problem, traveling salesman problem and knapsack problem, assignment problem. Okay, let's see about the selection sort. Here, let's move into the first sorting technique under brute force, which is selection sort. Okay, start by assuming the first element is the minimum. What we will do is we will assume the first element as the minimum, then compare it with every other element to find the actual minimum value. Once you have find it, we have to swap it with the first element. Move to the second position and repeat the process. This process is repeated until the entire list is sorted. Okay, it's simple to implement and does not require extra space, but due to its complexity, here we can see the complexity as order of n squared. Okay, one second. Okay, order of n square, it becomes insufficient for the large data set. Okay, we can see the selection sort algorithm. Selection sort example, let's look at a concentrate example to understand how the selection sort works step by step. Okay, here we start with the list 89, 45. Let me show you 89, 45, 68, 90, 29, 34, and 17 in first pass. The smallest element is 17, so it's swapped with 89. In second pass, the smallest element from the list is 29 is placed in the position 2 and so on. After every pass, we progressively build the sorted portion of the list at the beginning. Note that while the number of comparison remains the same, the number of swap is minimal, just one per pass, which is big advantage. Okay, next we will move to the bubble sort. Okay, here comes the bubble sort. This is another basic sort technique that embodies the brute force split. Here the concept, we compare adjacent elements and if they are out of order, we swap them. After the first full pass, the large element has bubbled to the end of the list. We repeat the process gradually, shrinking the unsorted section of the list. It is called bubble sort because of this bubbling up the numbers. Though simple and easy to code, it is insufficient in terms of both comparison and swapping, make it one of the slowest sorting algorithm. Okay, we'll see the example. Here we have the same example as 89, 45, 68, 90, 29, 34 and 17. First we will compare 89 and 45. Since 89 is greater than 45, we swap them. Continue this until the large element 90 reaches the end. In next pass 89, the second largest will find its place and so on. You will notice that the bubble sort make lot of unnecessary swaps, especially if the list is long or nearly reversed. That's why while it's educationally and easy to follow, we rarely use it in the real world application. Next is we'll go for analysis of bubble sort. Okay. Here Time complexity is order of n square across the bound worst, average, and even best case unless optimized with an early exit flag. Swaps are numerous, also order of n square, which means bubble sort can be very slow. It's great for teaching but not for performance sensitive application. Next, we will move on to the insertion sort. Here is an count of basic operation and summarization formula for your reference. You can go through this. Next comes the insertion sort. It is a technique that falls under a slightly smarter design approach, that is decrease and conquer. Think of it like arranging play cards in your hand. You start with one card already sorted, then one by one, you insert each new card into its correct position among the sorted one. We maintain two sections, one is sorted and one is unsorted. With each step, we reduce the size of the unsorted section and grow the sorted one. Okay, we'll see how the algorithm works. Pick the next element into the list. Compare it with the element in sorted session. Shift the element one by one until you find the right position for new value. Insert it there. Repeat this entire process until the list is sorted. Though it is also has order of n squared complexity, in the worst case it performs well on small and nearly sorted data. Okay, in analysis part, here we'll see the analysis of insertion sort. Best case already sorted list is order of n, only one comparison per element. Average and worst case is order of n square, like selection sort. It is in place and doesn't require extra money for extra memory. For small inputs, insertion sort is actually faster than more advanced algorithm like merge sort or quick sort. That's why insertion sort is often used as a base case in hybrid algorithm.